Just let me stretch out here. Always important to be nice and limber before you start an intense session of Twitch streaming. Setting up stuff on my phone. I try to monitor the chat on my phone just in case anyone joins the stream and drops comments in the chat, which occasionally happens. All right, so hello world. My name is Miles, and I'm a grad student at Michigan State University in the United States. And in my quest to become the world's biggest nerd, I try to learn the latest scientific discoveries by looking at the pretty figures published in top scientific journals. The papers I look at I've never seen before, and anyone who joins the stream is welcome to drop any questions or comments or suggestions of papers to look at in the chat, and I'd be happy to take a look at them. And please take a moment to subscribe to my Twitch and YouTube channels at Miles Does Science. It's free, and you can always unsubscribe later if you want. Now, as is customary for these episodes I run, I like to start by talking a little bit about climate change. And this is a paper I found about, I guess 5 minutes ago now, and it was published just, looks like just last week, actually, September 14th. It's currently September 20th, and in Nature, Ecology, and Evolution. And I kind of skimmed through the abstract here, and it looks like this paper, well, as the title suggests, it shows that tropical and Mediterranean areas are especially sensitive to losing species and biodiversity when under land use changes and climate change. It'd probably be helpful to just start with a nice definition of what biodiversity is. So biodiversity, as Wikipedia would tell you, is that it's a term to describe all the variety and, well, diversity of life found on planet Earth. And currently the Earth is undergoing massive losses in biodiversity, which is concerning for a number of reasons, but chief among them being that the diversity of organisms on Earth, well, they perform a lot of different functions that we as humans need to survive. And if biodiversity keeps declining, then eventually we are going to go extinct as well. There's a lot of interesting research always coming out about climate change, and I think it's especially important to understand it, even though I'm certainly not an expert in climate science or biodiversity loss or extinctions or anything like that. I do have a biology background, and I like to try to keep up to date on this area of research, since it's only the single greatest threat we face as a species. So let's go ahead and take a look at these figures here. Very nice, simple figures to start us off. Little simple dot plots with some error bars. Right away, we are bombarded with acronyms, as is pretty common in science. Something called PV, SV, PAS, and HRV. I think looks like those refer to different types of tropical forest biomes or something like that. Typically, oh no, it doesn't mean that at all. Typically, these acronyms will be defined in captions like these. So PV is primary vegetation, SV is secondary vegetation, PAS is pasture, and then HARV is areas of agriculture. I think it stands for harvested agricultural and then the error bars are 95% confidence intervals. So, okay, so in this panel A right here, we're looking at just tropical forests and measuring the amount of primary vegetation, secondary vegetation. I already forgot what PAS is, pasture, and then harvested agriculture. It's like change in richness. Hasn't been a change in richness in terms of the primary vegetation in tropical forest, but a stark decline in secondary vegetation, pasture, and harvested agriculture, which is interesting. So richness, by the way, when scientists refer to species richness, they just it's just a count of the number of species in an ecosystem. So yeah, that's all it means. So just the change in total species count, I guess this is trying to show. And I would have expected more primary vegetation loss, but oh well. Let's see here. And then this shows pretty much the same thing, but for tropical grasslands, not as much change for dry lands. And then some also large declines in Mediterranean areas for secondary vegetation. I forgot what PAS is again, pasture, and then harvested agriculture. Not many changes for temperate forests, and not as many changes for temperate grasslands. So already right away we can see the main takeaway in the paper, that there are more declines in species richness in Mediterranean and tropical forests than in other kinds of biomes. Okay, so those x-axes are land use types. Should probably read the title of the figure next time so I don't bumble through it. Let's see, I think there are 5 figures here, but they seem relatively simple, so try to not spend forever on them. Okay, so now it looks like we're looking at climate change more, because now we have change in species richness per degree centigrade. Is that like degrees centigrade of warming, or okay, so shown as the change in vertebrate species richness for each degree of climate warming expected under some scenario. I like to try to read out text because I know that it's probably kind of hard to read text on the stream. That's because my computer cannot yet stream in super high definition video, but I'm looking into getting a new computer, so hopefully that'll change pretty soon. Looks like we have different types of biomes again on the x-axis, and okay, so now we have box plots here which show distributions of data, not confidence intervals necessarily. Those can be easy to confuse. All right, so we have, looks like 7 different types of biomes. TRF is tropical forest, TRG is tropical grassland, dry is dryland, Med is Mediterranean, TEF is temperate forest, TEG is temperate grassland, and then BOF is boreal forest, which are those are kinds of forests that tend to be found at more northerly latitudes, and they don't have as much biodiversity as temperate forests and tropical forests. And so I guess what this is just trying to show is that, so typically in box plots, the black bar in the box shows the median of the distribution in richness change in this case. So I guess what this plot's just trying to show is that although the black bars can also be the mean as well, but typically they're the median. So typically, I guess what this plot's trying to say is that on average, there have been greater declines in species richness per degree of climate warming in tropical forests, tropical grasslands, and Mediterranean areas than these other types of biomes, which is kind of in line with their previous figure, except now they focused on climate warming instead of land use. Land use and climate warming are typically talked about together, it seems, because land use is how humans use land is a big driver of how the climate is changing, and biodiversity loss as well. So those three topics they're always presented in the same science sandwich, if you will. So looks like now we're looking at land use and climate warming simultaneously now. Very simple scatter plot. This is probably the simplest scatter plot I've ever seen in a scientific paper, only 6 data points, which refer to these 6 different types of biomes again. It looks like, let's see here. So this blue dot is tropical forest, the orange is tropical grassland, and then the purple is Mediterranean. And then the other data points are temperate biomes and dryland biomes. And you can see that generally these tropical and Mediterranean areas are experiencing greater declines in species richness change per degree of climate warming and per bit of human land use. So kind of just driving home the point that for every bit of climate warming and for every bit of land that humans use up, these tropical and Mediterranean biomes are hit the hardest in terms of biodiversity loss. I wonder if that could be just because those biomes have more biodiversity to lose, because tropical forests and Mediterranean areas are typically the biodiversity hotspots on Earth. I believe, back to my undergrad ecology courses. Go ahead and take a look at these line plots now. How are we doing on time? We're doing all right. Like 12 minutes in. Need to remember to check chat occasionally in case someone comes. Okay, here we go. Finally. Alright, so as always, so far they have species richness on the y-axis, and looks like now they have, not entirely sure what this is, temperature seasonality. Okay, so I guess it's some measure of how variable temperature is over the course of the year, plotted out by, oh man, this is kind of strange. What is it? Let's see what this means. So it's mixed effect models that temperature seasonality. I'm not sure what they mean by temperature seasonality. Because originally I was thinking like maybe this is time or something on the x-axis, but some measure of variance in temperature and precipitation respectively here, but I'm not quite sure why it's varying along this dimension. Let's see. Typically, the authors will define terms like these in the paper, so let's go ahead and do a quick search for seasonality. Did I spell it correctly? Okay, here we go. Tropical areas, they don't really have like temperature-based seasons. Like they're pretty warm all year round, aren't they? Although I think tropical areas do have like rainy and dry seasons, though. So let's see here. Climatic seasonality. Let's search for temperature. That come up. Come on. Okay, so it doesn't seem to be defined. At least I'm having trouble finding the definition, so not entirely sure. Not entirely sure what this figure is trying to convey, but we can go on to the last one. It looks like it shows the same thing. It has the same seasonality index. It's showing some correlations here between seasonality and change in richness. Okay, so maybe each data point here is like a different location or a different biome, and what they're trying to show is that, I don't know. Okay, so areas that have lower variance in temperature year-round, such as tropical areas, I presume, will have greater declines in species richness. Okay, that makes sense, and I guess a similar correlation here. Oh, this doesn't really look like a correlation at all. That's just like a cloud of points. And thermal position index versus precipitation position index, I don't know what those are either. Can obviously see that I'm not super well versed in these topics, but if I wasn't so lazy, I could probably Google the definitions real quick. But we're at kind of the halfway mark, so go ahead and move on to the next paper. This is pretty cool, though. It's a good paper. Yeah. I don't know if I might read it later. We'll see, though. But anyway, the real paper I want to talk about today is this one right here. Phosphine gas in the cloud decks of Venus. Now, this paper, published in Nature Astronomy, has made a really big splash in the news recently. If there's someone listening to this video at a later point, you may have heard it already from whatever news outlets you listen to. And essentially, I mean, the title here is pretty inconspicuous. Like, okay, so they found some chemical in the clouds of Venus. You know, what's the big deal? Who cares? Well, the big deal is that phosphine should not be in the clouds of Venus. If, as this abstract here says, the presence of any phosphorus compounds in the clouds of Venus should be oxidized based on what we know about the chemistry of Venus's atmosphere. Whereas phosphine is not an oxidized, compound, meaning that actually it may be helpful to show a picture of phosphine. Essentially, okay, so get a nice picture going. Dot structure maps. My computer continue thinking. Okay, so phosphine is this chemical right here. Pretty simple. It has a phosphorus atom in the center, bonded to 3 separate hydrogen atoms and a lone pair of electrons, I presume. So yeah, this is what I guess a chemist might refer to as a reduced compound, and that just means that it has lots of bonds to hydrogen in a sense, whereas an oxidized compound has many bonds to oxygen. So that's just kind of that's certainly not a rigorous definition of oxidized versus reduced, but that's kind of the idea. So the so to find try to explain why this phosphine gas is in Venus's atmosphere, and they weren't able to explain it using known abiotic production routes, meaning that as of right now, it is possible that there is some life form in the atmosphere of Venus producing this phosphine gas. All these scientists weren't able to explain phosphine production by looking at atmosphere chemistry, cloud chemistry, surface or subsurface chemistry, or incorporating lightning or volcanic and meteoritic delivery. So this is some very promising evidence that there could be some form of life on Venus. Now, it's certainly a long way away from isolating some microbe on Venus, or seeing little green men flying around in the clouds. But in terms of rigor, like this is some pretty promising stuff. So I thought it'd be cool to take a look at it. Looks like it goes into some spectroscopy and chemistry stuff that I'm definitely not familiar with. I have no background in astronomy, so I guess it'll be interesting for me to figure out what's going on here. So here we have some kind of spectroscopy observed with the JCMT. It's probably some telescope, I imagine. The L to C ratio, I don't know what that is. Venus frame velocity, I don't know what that is. I know what a Doppler shift is, but that's not going to help here too much. Let's see if we can Google what an L to C ratio is real quick. I might have to go kind of slowly through this because I'm not familiar with astronomy at all. Oh, come on, man. Oh, it's just what I was researching earlier. L to C ratio, astronomy. File is not found. What's going on with my internet? The internet's fine. I just typed something weird. LC ratio astronomy. I don't think Google liked the colon. Or I guess Ecosia. I use Ecosia. The other wasn't helpful. So let's try to find a figure that I can understand. I guess what they're trying to say, I guess they're trying to show some unique spectral signature of phosphine. I guess the basics of what they're trying to do is that different chemicals interact with light in different ways. Different chemicals absorb different wavelengths of light, and so I guess our unique signature of the wavelengths of light that a particular chemical absorbs is called its spectrum. And so I guess the authors here are they're just trying to show that there's something in Venus that has the unique spectral signature of phosphine. And it looks like that's probably what they're trying to show here too. They have some kind of LC ratio again. And to me it's just a bunch of squiggles and steps, but who knows? Maybe there's I imagine there are plenty of other people out there that could make sense of this. This looks a little more interesting. We have two spectra overlaying on each other. Before removal of final polynomial baseline. Yeah, I'm totally out of my depth here. But I knew I had to look at this because this is already turning into a famous paper. So it looks like they just have they have different spectra from two different telescopes, it looks like. And I'm not sure, I guess they're showing some kind of agreement between them. My spectroscopy is pretty rough. I haven't looked at spectra since, I don't know, since my last organic chemistry class. It's probably going on a year now, or two. Alright. I mean, I can look at more spectra, but I'm probably not going to be able to understand it. Estimating sulfur dioxide contamination of the phosphine line. Okay, so it looks like phosphine absorbs light at some specific frequency, and looks like sulfur dioxide may absorb light at a similar frequency, and the authors accounted for that potential contamination. But of course, they're not able to. No one has gone to Venus directly and detected phosphine in the atmosphere. So the authors have to do all this indirectly by looking at light. But it's good that they accounted for that, accounted for potential contamination. Let's see here. I think there's only one other figure that I won't be able to understand, but that'd be cool to look at. And typically, I only read papers in like genetics and evolution and topics like that. So astronomy and physics are just way outside of what I typically research. So the probability that I understand the figures from papers on those topics is much reduced. So photochemical production of phosphine found to be insufficient to explain observations. Okay, so here so I think what they're trying to see if a process called photochemical production can explain the presence of phosphine in the atmosphere. Photochemical production, I think that refers to just like sunlight hitting the atmosphere and the energy of that light causing different reactions. So just thought I'd confirm that real quick with a quick Wikipedia search. Okay, yeah, so photochemistry concerns the chemical effects of light. So essentially, how light itself can cause reactions. And I guess there's some process whereby phosphine can be produced by some other compound absorbing sunlight. But it looks like the amount of phosphine observed in the Venus atmosphere is far too high to be explained by this process, which is interesting. Very interesting. Looks like they're showing the rates of phosphine formation versus destruction by height in the atmosphere, I guess. Looks like phosphine is formed more often as you get closer to the surface, and I'm not entirely sure. I think it's destroyed more often as you go higher up in the atmosphere, perhaps. It looks like this is essentially what they're trying to show. Like, here's how much phosphine we observed, and here's how much we think is possible to be produced by abiotic means. And those two lines are very different from one another. And these kinds of disequilibria in atmosphere chemistry, we know are driven by life on Earth. So it's possible that there's some life form on Venus driving that disequilibrium as well. Although my guess is that it's probably some kind of microbe, if anything. It's unlikely to be, it's definitely not little green men or anything like that, or anything sentient in our typical definition, but it could be something incredible, something that no one's ever seen before. I'm just scrolling through these to see if there's anything I could probably understand. Okay, so LC ratio stands for line continuum, which has only confused me more. Some kind of chemical pathways are mapping out. Photochemistry modeling. Man, there are just lines everywhere here. That is a messy figure. Let's see here. Potential pathways of phosphine development. I just kind of listed those out. It looks like they were able to account for most of them. I don't know if they really accounted for these asteroid impacts or other potential sources. It looks like they accounted for quite a lot of them, which is good. They did a good job. All right, let's see here. How are we doing? All right, we just went over 30 minutes, so I guess this would be a good time to call it. Thank you very much for watching this video. If you made it all the way to the end, if anyone has suggestions for papers or questions, you can always comment on one of my YouTube videos, perhaps. We're on the same YouTube channel as the Twitch channel name. It's called Miles Does Science. All one word. You can look me up, and feel free to subscribe if you wish. And yeah, thank you guys very much, and have a good rest of your day.